Good afternoon. I'm Valeria Cuellar and I'll introduce you to the topic carbon quantum dots as mercury sensors. Mercury is a highly toxic heavy metal widely used in several industrial processes, including chlor-alkali production and battery manufacturing, which increases the risk of leakage and contamination of nearby water resources. In aqueous environments, mercury is a predominantly found in its ionic form mercury 2 ion. These ions can enter biological systems through dermal, respiratory, and digestive pathways, causing severe health effects such as central nervous system damage, DNA alteration, and disruption of cellular division processes. Furthermore, mercury is highly persistent in the environment, exacerbating its ecological and public health impact. Consequently, the development of accurate and sensitive chemical methods for mercury 2 ion detection has become a major priority in environmental science and public health. In recent years, carbon quantum dots have attracted significant attention and sensing materials for mercury detection. But what exactly are carbon quantum dots? Carbon quantum dots are fluorescent nanomaterials with particle size below 10 nanometers. These materials exhibit remarkable properties, including strong and tunable photoluminescence, high water solubility, excellent biocompatibility, and high resistance to photo degradation and photo bleaching. Unlike other quantum dots synthesized from heavy metal precursors, carbon quantum dots are more environmentally friendly and exhibit low cytotoxicity. In addition to these properties, carbon quantum dots can be functionalized through doping with strategic biomolecules, enabling improvements in solubility, biocompatibility, and most importantly, optical performance. These processes allow modulation of fluorescence behaviors, correction of structural defects, and enhancement of emission intensity, thereby improving their applicability as optical sensors for contaminants such as mercury 2 ion. Under visible light, an aqueous solution of carbon quantum dots typically exhibits a yellow to brown coloration. However, upon exposure to ultraviolet radiation, carbon quantum dots generally emit a bright blue fluorescence. The fluorescence of carbon quantum dots originates from electrons transition from bonding orbital to anti-bonding orbital upon energy absorption. Subsequently, the excited electrons return to their ground state, releasing energy in the form of visible light emission. This electronic transition primarily occurs within carbon double bonds and oxygen and nitrogen containing functional groups located on the surface of the carbon quantum dots. As previously mentioned, carbon quantum dots can be functionalized through doping, with nitrogen being one of the most commonly used heteroatoms, due to its ability to enhance the optical properties of the materials. An example of this was reported by terrorists and co-workers, who synthesized carbon quantum dots using lemon citrus juice as a precursor and ethylenediamine as a doping agent. The authors can observe that nitrogen doping increased the quantum yield, a parameter associated with photoluminescence efficiency, and improving detection selectivity toward different analytes. But how do carbon quantum dots detect mercury? Well, several studies have demonstrated the effectiveness of carbon quantum dots for mercury 2 ion sensing through fluorescence quenching mechanism. This phenomenon occurs due to the interaction between mercury 2 ions and the functional groups present on the carbon quantum surface, particularly carboxylic groups, which facilitate electron transfer and suppress fluorescence emission. According to theories and collaborators, the sensing mechanism of nitrogen-doped carbon quantum dots is based on the interaction between oxygen and nitrogen-containing functional groups and Mercury-2 cations. These functional groups exhibit a strong affinity for mercury ions and form coordination bonds through electron pair donation, leading to fluorescence quenching. On the other hand, Risby and co-workers characterized their synthesized carbon quantum dots using techniques such as Fourier transform, infrared spectroscopy, ultraviolet visible spectroscopy, and transmission electron microscopy. Their findings indicate that positively charged Mercury-2 ions interact with negatively charged carboxylic groups on the carbon quantum dot surface. These interactions result in the formation of unstable carbon-mercury complexes, which subsequently converts into mercury-oxygen compounds, ultimately causing fluorescence quenching. Additionally, these authors evaluated the selectivity of carbon quantum dots toward different metal ions. Various cations were added to fluorescence carbon quantum dot solution, and only the carbon quantum dot Mercury-2 ion system exhibited a significant decrease in fluorescence intensity within the first 7 minutes of observation. This behavior demonstrated the high selectivity of carbon quantum dot for Mercury-2 ion detection. Similarly, theories and collaborators reported that only iron-3 ion produced a slight decrease in fluorescence intensity, although this effect was negligible compared to that caused by Mercury-2 ion. Therefore, they concluded that nitrogen-doped carbon quantum dots can serve as selective fluorescence probes for mercury detection in aqueous solution. It is important to highlight that these nanomaterials exhibit detection limits in the nanomolar range, making them highly sensitive sensors capable of detecting even trace amounts of Mercury-2 ions in water. In conclusion, carbon quantum dots represent an efficient, sensitive, and environmentally friendly alternative for mercury detection in aquatic systems. Their ability to identify trace concentration of Mercury-2 ions highlights their potential to bridge chemical innovation and environmental protection. Continued advancement in this field will be essential for improving real-time water quality monitoring and safeguarding public health against heavy metal contamination. These are the references for this work. Thank you for watching. Now, I'll be happy to answer any question you may have.